today we're going to look at RAG, which is Retrieval Augmented Generation. And we've mentioned this in a few of the past question answering discussions. And this model came out last year. It's not necessarily the best question answering model, but it's quite good. And Hugging Face has an implementation. There's also a Haystack implementation. And a little later, we're going to look at both of those, and I have some code examples. So it's sort of the most accessible, out-of-the-box question answering system that is close to state-of-the-art. It also, for kind of education purposes, contains a lot of the core ideas that we've discussed in past discussion groups, namely having a retriever and a generator, and using this to, given some question and a group of documents, be able to answer questions in a way that is generative and not extractive. So extractive, as we covered in previous things, is something like finding the document that you think has the answer to your question. If I ask, what is the population of Paris? And my document is a Wikipedia article on Paris. The extractive approach is just to take that document and look for a specific sequence that it thinks is the correct answer to that. So it might scan it and it will find that exact part and it will pull it out. And that's a great approach, but sometimes the question is a little more nuanced or tricky and the answer isn't contained in one document. So if I ask, what is, the president's sister's dog's name, in the president's Wikipedia page, it doesn't necessarily have his sister's dog's name in there. And in, the sister's Wikipedia page, let's just say it has the dog's name. So you have to be able to link one entity to another, and then inside of that, find the answer. So that's called multi-hop, and it basically means it's impossible for an extractive reader to figure that out unless it's explicitly stated. So generative question answering, like RAG, is a little more experimental, but has more promise in the long run of being a sort of very robust human-like question answering system. So RAG is one of these systems. We'll just go briefly over the components of RAG, which we've discussed in past discussion groups. So you can check that out in the previous YouTube videos. And I've just basically pulled the notes from those sessions. So the retriever, and just for context, this is composed of a retriever and a generator. And the retriever is there simply to take your question, look through a bunch of documents, find the most similar ones, and then the generator wants to use those documents and your question to try and come up with an answer. So really, you can use any retriever in your kind of question answering system. In RAG, they use DPR. And DPR is very simply two little BERT encoders. They're not full size, just for the unwieldiness. The questions, this is the training regimen. We take a question and a context which match. We encode the question, and we encode the context. We feed these through. We take the similarity, or the dot product, and we want to optimize both of these such that similar question and contexts have a high similarity score, and those that are unrelated have a low similarity score. So essentially, we're just encoding these pieces of text, but we're also trying to get them to learn something about similarity. So we're gently fine-tuning them to be good at recognizing similarity. So a trained DPR is just a model that's this structure that's been through this quite a bit, and in theory it has a good ability to determine whether two pieces of text are similar. And the similarity is a good kind of proxy for whether or not the question can be answered by the context. So two highly similar pieces of text are more likely to have a question-answer kind of correspondence. And that's the idea. All right, our generator is BERT, but again, you can use any kind of sequence-to-sequence generator, anything that's taking in input text and giving out output text that's generated on the fly. So BERT I was a little confused about the details, I think last week when we talked about this. It turns out it's really the exact same architecture as the transformer, but they just use a different activation function. So there's a lot of discussion in the paper about what it's doing and what the strategies are, but architecturally it's nearly identical to just the original transformer architecture. So I'm not going to add too much about that because there's lots written about the transformer architecture. The thing that distinguishes it is really having a somewhat unique pre-training task. So they kind of throw a bunch of different pre-training tasks at it in which they're masking input words in different ways and asking the model to then predict what those masked words are, or it's asking it to auto-regressively understand and fill in the word that is missing from a sequence. So it's really just a kind of a training regimen they created, but the real idea is that this pre-training task creates a model that is good for language generation. And so that is sort of the idea, and the takeaway is that BERT is the pre-training regimen makes a fine-tuned BERT model quite good at language generation specifically. So it's a good candidate for a generator.
Do you know how the pre-training task compares to it kind of sounds similar to Electra, where they randomly swap out some of the words, and the task is to what is it? It's to predict whether the word is correct, each word is correct or not. Is that right? Something like that.
Yeah, that was the Electra, sort of like a pseudo-adversarial kind of task.
So this sounds kind of similar because there's corrupted text.
Yeah, I think the difference is that in Electra, it's not strictly adversarial, but there's a generator, and it will try and fill in a suitable candidate for some of the words, and then the discriminator on the other end has to basically, the idea is it's very efficient because for each word, it has to guess whether or not this one is an original word or it's been swapped out by the
generator?
Yeah.
Okay.
So this, I think, is just it's probably in the notes of last week, but I think it's just a more kind of straightforward denoising task where they add some noise and they ask you to recover the noise.
Is it, let's see, BERT inputs the encoder. I mean, looking at the illustration, I guess it looks like they're doing masking. Like they're okay. So instead of swapping out words, they're masking out words.
Yeah, and I believe it's asked to recover what those masked out words are instead of saying, is this a original or a fake word?
Gotcha.
Yeah.
Cool. Thanks.
But the pre-training tasks in the paper are there, and I think it's just, you can come up with any kind of many different varieties of what the pre-training task should be, and these ones happen to create a model that's good at language generation.
Cool.
Yeah. Okay, so these are the two core components to RAG. So we have, this is their diagram of the entire system, and one of the advantages is that this whole system can be trained end-to-end through backpropagation. So that means training both your fine-tuning, essentially, the BERT generator, and you're also fine-tuning the query encoder, which is half of DPR. So we'll look at that in a little more detail, but if you want to get a good overview of what this is, just very briefly. This illustration from their paper, they also create a blog post, is a good way to kind of just sit with it and look and figure out, oh, okay, kind of see what's going on here. So the focus of this model is, again, a lot of the point is using non-parametric knowledge. So in this case, and for the kind of standard RAG, they use Wikipedia. And so they want to be able to ask the system a question and give it a big index of Wikipedia documents, and then be able to get an answer that is contained in those Wikipedia documents, as opposed to just relying on the kind of parametric knowledge of a generator, where BERT might, because it's been pre-trained on so much text, it just kind of knows some factoids just by seeing the statistical similarity of certain things, of seeing the same piece of text over and over. It can do an okay job of kind of generating answers, or sometimes it kind of hallucinates what the answer is because it's just going word by word, maximum probability. So it's not always right, but this is essentially an attempt to augment the parametric knowledge with non-parametric knowledge. So we'll kind of run through what a piece of text does as it goes through. So we start with a question and a number of reference documents. So we'll just call the documents Wikipedia in this case. In the beginning, you have your DPR, and you feed all of the documents through the document encoder, and you pre-compute all of these vectors for the documents. And this just makes it easier to then test a query against these specific documents. So when you feed in the question, you feed it into the question encoder, which again in DPR is just a BERT encoder. You come up with a BERT vector, and then against all of these document vectors, also encoded by a BERT model, you find the maximum inner product. So maximum inner product search is essentially looking for the cosine similarity of your question to each document and taking the maximum. And for this, we really talk mostly about top K, because you don't necessarily just want to look at one document. You might want to look at 5 or 10. You want to use kind of all the evidence you can get. So essentially, you're finding the most similar documents to your question, and those are kind of the best candidates for having the answer. So then, and this is a question we had the other week, you concatenate the raw text of the question and the raw text of the document. And you basically concatenate those together, and then that is what you're feeding into the generator. So that allows the generator to just work as sequence to sequence. Basically, the pre-computed document vectors and the query vector are just used to find the most similar documents. So after this stage, the retriever is done. The goal really of the retriever is just to find the raw text documents that are most likely to contain the answer to your raw text questions. So we concatenate those, and we feed it into the generator. And the generator produces from there its answer. And this system, when it was just smushed together as DPR and BERT, might not produce very good answers. But RAG itself is a pre-trained system. So they fed in a lot of question-answer pairs, and over time, this generator has been fine-tuned to be able to answer questions. So when you download a RAG sequence model, it's already sort of been through a question answering fine-tuning. So in the end, you come out with an answer to your question. And this answer is generated, and they sort of have two models, and there are two kind of strategies for doing this. Let's see. Yes, and we'll get this a little later, but just the decision they made by design is that the document encoder doesn't get updated in backprop because it would be really expensive when they're training this model end-to-end to each time update the document encoder and then basically recompute the entire document index. And when we run this example, it takes a good amount of time just to load the index of pre-computed Wikipedia vectors. So if you had to do this at every iteration of your training regimen, it would be really expensive. And it turns out that just using a plain DPR document encoder works pretty well. You don't really need to fine-tune it too much on the question answering. You don't really see a loss in accuracy. So the document index just stays as is. The only encoder that gets updated with pre-training and backprop is the query encoder. And that's much less expensive because you're just doing one query at a time. All right, so we'll get a little into the best way to kind of look at what it does and how it computes the answer is to look at a little of the math and the equations that produce it. I don't think I'll spend a ton of time on this because it's I think I had to kind of sit and stare at it for a little while. I'll probably, when we're kind of presenting this in a more concise fashion, it'll be a much more kind of exploded and detailed version of what's going on. But I'll just sort of talk about it, and you don't necessarily have to look at the math if you're not comfortable with it, or if you are, the math is right there, and I've labeled what the variables are. That's coming up in just a second. But I'll first talk, and these two equations basically detail to the two models that the authors made. So there's RAG sequence and RAG token. RAG sequence basically takes each of your top K documents, and from within each document, it creates an answer. So you would look at document 1 and your question, and you would come up with an answer. And then document 2 and your answer, and you'd come up with a question, or an answer. Document 3 and your question, and you produce an answer. So you're producing an answer for each of these separate documents. In RAG token, you're doing it token by token. So essentially you start with your first token, and then instead of sticking with the same document, you look over all documents to find the most likely next token. And then for the third, you look at both the first two tokens you've generated and all of the documents, and you try and compute from there what is the most likely third token given all of the documents in the first two words in your sequence.
So looking at all of the documents, does that mean like concatenating all of them together on the input, or?
No, it's looking at the kind of probabilities of each of all of the combinations of your sequence and the question in document 1, your sequence and the question in document 2.
So it's generating a probability for basically every token in every document.
Yeah.
And the highest one.
Mm-hmm. Yeah. And this talk by one of the RAG authors, Patrick Lewis, is it's a good overview, and he kind of discusses it for the first 20 or 30 minutes or something like that, and then goes into kind of the results of the system. But I've sort of nabbed his slides because they have a nice picture of the actual equations. He's done a tiny bit of labeling. So yeah, I don't know how much fun this is or how helpful this is to talk through, but essentially these are the names of the variables, and you can see all of this in the paper. And these are the training equations used. So briefly, just to kind of give a 2-minute overview of these, if we're looking at, say, the sequence model, you want to find the probability of the answer given the question, and that is equivalent to For all of the top K documents, the probability eta of the document given the input sequence, this whole term is really just the similarity score. So each time you're kind of trying to generate a token, you take into account and weigh the similarity score that was created between your question and the document. So you can see why that's a nice idea. And as you're training, this eta is sort of a parameter over the it's a parameter over the question encoder. So this updates the question encoder and hopefully brings it to a better similarity for question answering. So the probability of a given word is then the word given the sequence and the document, or the question and the document. A RAG token, basically you're doing the marginalization over each single word here. So once again, the probability of the document given the input sequence times the probability of word I given the question, the document, and words 1 to I minus 1. So all of the sequence up to then. What is the probability of that word? Well, it's just the probability of that word occurring from document 1 plus document 2 plus document 3. So you're really just trying to answer, if you have 10 documents, if you want to figure out, well, what's the probability that this is the next word in the answer? That's just the sum of the probability that it's the probability that given document 1, that's the next answer, plus the probability given document 2, that's the answer. Yeah, so, so that's a little, you have a
couple of questions, Nick. So the probabilities are calculated based on the vocabulary of the model. Is that right? It's like it generates a probability for every word in its vocabulary.
Yeah.
Okay. All right. And then you're saying that in order to compare the different words in the vocabulary to see which one is the most likely, you actually sum up the probabilities for each vocabulary term for all of the documents.
Mm-hmm.
Okay. And that's and we're looking at, we're talking about the RAG token approach.
Yeah.
Okay. So then how was RAG sequence different again? Let's see, RAG sequence was generate a separate answer per document. Okay. Yeah. So the RAG sequence is almost like, is it really almost like it just operates on one document, but you just generate answers for all the top K documents?
Mm-hmm.
Does that then mean that it can't incorporate information from multiple documents? It's like it's not a multi-hop question.
Yeah.
Okay.
And there's again, this is, hard to talk through in a short amount of time.
Yeah.
I don't know that it helps too much, but, if you're interested, I think it might help to just kind of look at it, and I've labeled most of the components of the sequence.
Yeah.
Maybe help you out a little.
Definitely. Yeah, it's really helpful to have the variables labeled.
It does, doesn't it? Yeah. But yeah, I think if we want to make a concise version, we'll actually create some kind of exploded out version of this equation that shows in a little more detail what's going on.
Kind of like there's an ebook here. Like,
yeah,
there's a lot to there's a lot to cover about the real details of how these two models work.
Yeah. And this is just for the training regimen. And so decoding is sort of another question. And with the RAG token model, if you're familiar with beam search, this is really just the idea that you start with one word, and given that word, you look at a series of hypotheses. So you sort of branch out from that first word, and then you take the most likely of the second word, and you're basically pathing a tree among all the possible hypotheses to find the most likely answer. So a very standard beam search is what's used with RAG token model. In that, here this term is just the standard kind of, and it's followed here. It's the very intuitive idea of how you generate a sequence one word to the next. The whole term is just saying the probability of your sequence is the probability of the first word multiplied by the probability of the second word given the first word multiplied by the probability of the third word given the first two words. So in that way, you can really kind of, when it's time to answer a question with the trained models, you can decode in this kind of straightforward way. And the RAG sequence model has a much more kind of complex way of decoding answers. So it looks, again, I'll do this briefly. It looks a little bit like, so we're given one document and the question. And from here, say we generate two kind of hypotheses about what the first word is. What we really want to get over here is the probability of that hypothesis given the input sequence. But we kind of have this middle variable of looking over all the documents. So what we essentially do is multiply the probability for hypothesis 1, let's say, multiply the probability that it's found in document 1, document 2, document 3, and then you multiply that by the probability that you do get document 1 given the input sequence, that you do get document 2 given the input sequence. And so the answer that you're looking for here, which is the probability that given the question, you're getting this hypothesis Y11, is just the sum of the probability that you get it from document 1 plus the probability that you get it from document 2 plus the probability that you get it from document 3. And that's kind of how you recover these probabilities. And from there, you just take the highest probable output sequence. So again, if this interests you, you can look at it in your own time. If it doesn't, then we'll have a more kind of exploded out kind of internal look at how this is doing what it's doing with more real examples and sort of better labeled equations that can help you get a grasp on this.
Hey Nick, sorry to interrupt, but
Yeah.
it's fascinating discussion. I missed the point of how is the output different from RAG sequence versus RAG token? Like what things would be different if I plug replaced one for the other?
Yeah, and this is really the takeaway point when you're looking at these two models. RAG sequence will produce an answer, but it will only produce an answer from a single document. So, if you ask a question and it's about the president's sister's dog, to take our amazing example, it will only be able to answer and generate an answer from one document that the retriever has recovered. Whereas RAG token, it can actually, each word it generates, it'll look over all of the documents and say, what's the most probable answer for this next document? So RAG token is a little like, at each step, it again scans all the documents and tries to find the most probable word.
Okay, so it could be that RAG token comes up with the most original answer.
Yeah.
But less accurate because it doesn't come from a particular body of text that's kind of been created together.
Exactly. It's this trade-off of it seems very good for multi-hop, and it can come up with a very original answer, but the trade-off is it might kind of jump a little all over the place because it's, pulling its first two words from this article and the next two words from that article and the fifth word from a third article.
That's great. So it could be that RAG token is good for a conversational bot, but not so much for an accurate bot if you're just trying to get a factual answer.
Yeah, true.
Good. All right, thanks.
So when you say like taking a token from a different document, you don't mean like extracting a token. Yeah, because I think I was confused at first because it maybe sounded like you're talking about like pick this word from document A and then like the next word is this word from document B.
Yeah.
It's
on the vocabulary. Yeah.
Right. Okay. Yeah.
But it's as the kind of informing variable there, it's either using, all of the documents or a single document.
Yeah, and then it sounded too like it does actually, it doesn't really like just pick a token, given a particular document. Like it includes the probabilities. So let's say for the dog, the dog's name is Sparky. Like it produces a probability for Sparky from every document. And then the probability of choosing Sparky as the next word in the sequence is somehow like a combination of all of those probabilities plus the retrieval score. Is that right?
Yes. So it's very, in any kind of decoder, really you're looking at just this function, right? And this is a little more straightforward, just this term, which is just generating the next word given, the input, the previous words, and in this case, the document. So in both of these, you're really just doing a different way of incorporating the fact that we have separate documents. And you can't really, if the document is used as your input, it's apples and oranges to try and say, the highest probability is coming from, the highest probability from document 1 versus the highest probability from document 2. It's not clear how to compare those in a fair way. So this is just this term, and this marginalization of our documents is just the way that we try and kind of account for that.
So does marginalizing, does that just mean like combining the probabilities across all documents?
Mm-hmm.
Okay.
Yeah, marginalizing is more or less trying to recover the thing you're interested in if it's spread over kind of multiple middle variables. It's basically trying to recover that probability.
Okay. Yeah. So I'm trying to think then like what the disadvantage to RAG token is. Because it sounds just better and smarter really, but I'm guessing it's just like it's a more ambitious task maybe. So
yeah, I mean more expensive certainly because it's doing this like way more expensive. This isn't even they do a pared down version of this because this is so kind of onerous, where they eliminate some of these probabilities having to be computed, and they just set it to 0 and there's minimal loss. So RAG token is more expensive. And in the outcomes, I can't remember which kind of has the edge. It might be RAG token, but they're pretty similar in terms of scoring on different benchmarks. And I'm not sure, it really might depend dataset to dataset, where you could imagine a case where among your kind of knowledge dataset, the answer would really only be in one, like you would just really not have kind of multi-hop scenarios.
Hmm.
You know, if you just had, if you were trying to answer questions about different engine parts and you had a fact sheet for each engine part, it really, you know, you wouldn't necessarily want to use a RAG token model because I don't want it getting confused about, seeing some words here and then going to another kind of document to find that. I'm really just interested in the fact sheet from my one engine part. So the RAG sequence model might make sense here. Like I know the answer is just going to be in that one document.
Yeah. Do you think that's true to the point that like RAG sequence might be more accurate in those cases? That like RAG token might just it's more, you're just creating the chance for it to get confused.
Yeah, you're giving it a little chance to kind of, it's both expensive and, I don't know, this is sort of speculation. We can look at the results of the paper, but a little bit more chance to find an answer that's not correct. So maybe like confident false positives are much higher with token than with sequence.
That does seem like it's the case. Sequence is going to be better for accuracy, but token is going to be better for conversation, just to kind of keep it going. But it's kind of like it might be the BSer, but the BSer everyone pays attention to.
Very true.
Interesting.
Yeah. So again, if you're interested in the kind of details of this, we'll have some kind of more spelled out diagram where you can look through and see what's going on. It's, as I'm finding, a little difficult to just talk through what this is because there's so many kind of moving parts within one. All right, so we've got a little time. I'll share a couple of Collab examples. Let's see. There we go. So we have one Collab example that I created that is using RAG from the Hugging Face implementation, and it's implementing your own data set. So we'll go to that right here. And Hugging Face, and here's a link to the, they have a kind of research project with RAG, and it has a script for using your own data set and for fine-tuning the model on your own data set, and a couple more kind of utilities. There's also a good blog about fine-tuning this with Ray, which is it's a library for distributed kind of computing, and they just found that using this as opposed to the kind of implemented torch parallel computing that was provided provides like a 2x speed up or something like that. So they have these kind of scripts built in that will let you run these things. We'll create, just for this library, or this collab rather, we're just going to kind of look at what this does and give you a kind of more open way to experiment with this instead of just simply running the script and then coming out with a computed model. So this is a little more flexible. And note that this took a little while for me. If you want to run RAG, even using the Hugging Face documentation, just example code of load the model, ask a simple question, get an answer. You need to install all of these dependencies. So it will tell you need transformers and data sets, but after you install transformers and data sets and load them, it simply won't work. So it took a little while to find out, and there's no error message that you also need face CPU and PSUtil to make any kind of RAG example run, as far as I've seen. So hopefully this is a real time saver for anyone interested in trying this out.
Hey, Nick, is this your comments or is this on Hugging Face that we need those additional sets, the additional dependencies?
Oh no, this is mine. They have a requirements text in this Hugging Face RAG project, which includes
Right.
these.
Oh,
But in the
okay.
kind of Hugging Face documentation, they give you,
Oh, okay, right. So it's in the requirements, but they just didn't post it on the description.
yeah, and it's not really in the, unfortunately, it's not really in the error message anywhere. So if you try and take this example code and run it, it won't work and it won't really tell you why. It just says you need data sets or something like that.
Oh, okay.
So yeah, so make sure to include these additional dependencies.
Right, so thanks for the heads up.
Yeah. Okay, so I'm not going to run these live because they take quite a while to load. In particular, I think the Wikipedia index takes quite a while here to tell me how long it all took. No, but it was maybe 10 or 15 minutes to get this running. I don't have a GPU attached to this just because it's a demonstration notebook, but maybe if you attach a GPU, I don't know why that would necessarily help speed up just the loading of the model, but maybe when it's time to actually ask a question, it does this well.
So Nick, where does the document store, or where does the corpus come into play here? I'm guessing it's like the RAG retriever model, and it was like the RAG retriever. Does it kind of have the Wikipedia data set built into it?
Yes. So it's not built in, but when you call, it's just an argument that Hugging Face is used. When you call use dummy dataset true, in this case, dummy dataset is just the Wikipedia dataset that they used for, the authors used for training RAG. So if you make this call, then it will retrieve the Wikipedia kind of dataset.
Which is massive, or do they have kind of a pared down?
Yeah, it's not the full one. It's pared down, but it is loading both the text and the pre-computed. These are face indices, yeah. So it's loading both the text and the index, because it has to use the text to feed to the generator. So it takes a little while. It's not the full thing, but it's a pared down version. I believe each document is 100 words, which is just a kind of practical but useful idea about when you're loading these sequences in, to try and not get your sequences too long. So the authors have, for the Wikipedia example, they might have, the kind of idea is probably you take a Wikipedia article and you break it into chunks of 100 tokens each. And this just makes it a little easier on the generator when it's time to create an answer.
Interesting.
We had that question last week of, why wouldn't you constantly run into these
sequence length problems? Yeah,
exactly. So their answer is just to create little kind of mini chunks of a document.
Gotcha. And so the big picture of this notebook, first few cells here, you're using the dummy index Wikipedia, but then lower down, you actually create an index for a custom data set.
Mm-hmm.
Cool.
Exactly. Yeah, so this is just testing RAG on the provided Wikipedia data set, just so you have kind of the code to see what it's doing, and it's Hugging Face, so it's pretty straightforward. You load the tokenizer, you load the model here, and you have to set the retriever to this retriever, and you're loading the retriever, and really this is kind of the part you need to pay attention to. And in this case, this is loading the Wikipedia data set, and later, further down this notebook, when we use the retriever, we're essentially swapping out this with our own data set, and then loading it into the model So this is just kind of generation code to show you, now that we have the model and the tokenizer and the retriever loaded, you ask a question, you have to ask the model to generate specifically, and then you get an answer. So how many people live in Paris? 270 million. Seems quite wrong. But this was their example. Okay, so I won't walk through a lot of this because a lot of this code is simply pulled from this use own knowledge data set. But if you're interested in implementing your own example, have a look through this. And I've basically just flagged kind of the 1 or 2 points where you need to kind of implement your own data set and put it in. So the scripts, you need these are just kind of text processing functions that are used for creating a face index of your data set. These are just kind of processing arguments. And really what you need to do kind of on your own, and I have a bit of code to help you with this that I can add into a more finished notebook, is you need to get your custom data set into this very specific format where the first column is title, the second column is text, and the title doesn't matter, it can be numerical, and the text is your text documents. So you need to create a CSV with these very kind of specific parameters, and this is how the next portion, which just wants to convert this text into a face index and be able to refer back to the text when it's time to feed to the generator. This is just the format it requires. So let's see here. This is the parameter you need to pay attention to, and I'll highlight this a little more. And here we've simply added, instead of the default Game of Thrones dataset.csv, which is just in my local file.
Is that something that's available out there, or did you have to do some work to kind of assemble that, like scrape the wiki or something?
It was actually stolen from the haystack example.
Oh, nice.
I think it's a series of documents that's a summary of each episode, like a 500-word summary, but they just treat those as the documents. But you can use any document example you like, any data set. So yeah, I'll highlight these kind of as the few variables you need to change, but otherwise you're just creating from your text data set a face index that the model knows how to use kind of out of the box. And then here, again, with a few parameters.
For anyone that doesn't know, like Nick and I have a lot of experience with this library, but FACE is like the Facebook AI similarity search library. So it implements approximate nearest neighbor techniques to do fast KNN or maximum inner product search, as they seem to be calling it now.
Mm-hmm. Yeah. And this, all of this, again, all of this code is really just to take your data set and convert it into a face index, just a easy to compute vector space, and then use that to then try and find the most relevant documents to feed to your generator to answer questions. So this is really all the sample code, and yeah, I'll clean this up a little bit so it's very clear where exactly you need to put in your custom data set to get this to run. Yeah, and at the end, again, we have kind of, here's some code to help you ask a question and get an answer in a short amount of lines. We're almost out of time. I have linked here. This is an example from Haystack. And And so Haystack is, both the organization is called DeepSet AI, but Haystack is a kind of question answering ecosystem, and they have a bunch of models and tutorials, and more importantly, it's kind of a more productionized pipeline. So they provide you with Elasticsearch and kind of fast indices and all these kind of tools to help you kind of plug and play your own question answering model. I haven't used it in too much detail, but it looks like another good place to get started. So they have their own RAG tutorial that you can take a look at. So if you're interested in maybe a more faster productionized version, you can try out Haystack. I don't know how much you're able to kind of dig into the details or change too many of the parameters, but it's something worth looking at. I don't see an ability to fine-tune in Haystack your RAG generator on your data set, which is something Hugging Face does allow, which depending on the interest, we might provide some code for. Hugging Face provides a script, but maybe something a little more cleaned up that explains what's going on. If that's helpful to anyone, we can create. So yeah, hopefully that's helped explain a bit of what RAG is, and maybe more importantly, giving you some example code to play with, where you can both test out the RAG model on the Wikipedia data set, as well as kind of implement your own. And I forgot to add, Hugging Face also created a live demo where we can ask questions. So it's essentially a live demo of the Wikipedia included Jeopardy. It's just a live demo of the first few lines of code that I have in the notebook. Can I ask my own question? I can. So if you feel like playing around with that, there's a kind of nice interface.
It looks like if you do free input, it looks like it creates a second text box. Is that right? For inputting your question?
Here it is, yes.
I Googled that question. It's like 2.1 million.
Yeah, okay, here we go.
Yeah. I bet 270 is like the population of France or something like that.
Yeah, a few too many.
Just, a couple orders of magnitude off, but it's machine learning.
Oh yeah, what do you want?
It's fuzzy.
Well, that's good news. This one does better than, maybe it's because we're using RAG sequence. Oh. Oh, one of these is RAG token, one of these is RAG sequence. Well, either way, a more reliable demo. You have the Hugging Face one here.
That's cool. So that first notebook you shared is basically the script from the Transformers library, but kind of like changed into Collab notebook form. And then what do they use as their example data set? Do they have I'm looking through the script now. I was trying to figure out if...
I don't know if they provide one.
Oh, okay. It's like...
I think they're just saying...
you sit in on the command line or something.
Yeah, exactly. So they really just give you kind of this... yeah, so they specify what this should look like, but I don't think they give you an example data set. But it's just a script that you can run if you're interested.
Nice. Cool. Yeah, so we could probably clean that one up a bit, like add some more clarifying comments to it and share that, I'm thinking.
Mm-hmm.
So it's basically their script.
Mm-hmm.
But, yeah. Nice. All right. Yeah, I think we can go a few minutes over here since we started kind of late.
Mm-hmm.
Any questions, guys? I think we've been asking them as we've gone, but
No, this is great. Thanks, Nick, for walking through.
Yeah, great discussion. I really appreciate it, Nick and Chris. RAG is real interesting. Appreciate it.
yeah, it's a cool model. Great. Well, I think we'll wrap it up there. And yeah, next week I'm planning on sharing some more stuff on the categorical features stuff. I'm going to show the approach of like concatenating the features using a custom BERT class. So hopefully see you guys next week. Thank you.
Very interested.
Thanks, everyone.